Okay, the next part, 5.9, is actually all about preparing salts. And since salts are both soluble and insoluble, and when I say that, remember our table on page number 137, this entire big table is very important to remember which salts are soluble and which salts are insoluble. By the way, this table is also explained in the study tip, which I skipped yesterday intentionally because it's better to not to go with the study tip instead to go with the table and remember the exact name of the insoluble salts, in some cases for chloride, sulfates, or carbonates. That's why I always ask my students to prefer this table instead of preferring this study tips. So that's why you can simply skip the study tips. Now, since we are at it and we're talking about salts being soluble and insoluble, so definitely preparing soluble salts will have different techniques. So this 5.9 is all about preparing soluble salts, which is again bifurcated into two methods, as you can see a heading right below it for method A. If I move on a couple of pages and get down to page 140, you'll see method B. Okay, after we are done with both methods A and B in detail, you'll see that 5.10 is about preparing insoluble salts. So yeah, we are supposed to prepare both kinds of salts. It's just that we're going to first start with preparing soluble salts. Okay, so let's come back to page number 138 and let's start with preparing soluble salts. Now, if we are supposed to prepare soluble salts, something that I we can say easily is that preparing soluble salts is pretty much related to the characteristic reactions of acid. Okay, so I'm going to use the space at the bottom of page number 38. Now, whenever we talked about different reactions of acids, we actually had three categories to talk about. Now, the acid was capable of reacting with a metal, and it then gave us salt plus hydrogen. We have done with it in 5.8, so 5.7, so it should be easy. Then the acid was also capable of reacting with either a base or an alkali. And in both the cases, it was capable of giving us salt plus water, H2O. And the acid was capable of a third and last type. This was the first kind, this was the second kind, and this is the third kind of third characteristic reaction in which it was capable of reacting with the metal carbonate. Now, when it reacted with the metal carbonate, it gave us salt plus water plus carbon dioxide. All right. So that's how we bifurcated these. Now, out of these or reactions, let me tell you, and I'm going to use a different color for your ease. This is going to be a part of method B, which is not this one, which is given on page number 140. And all of these, this metal, this base, and this metal carbonate, they're all a part of method A. Okay, method A more belongs to crystallization technique. Crystallization is a technique that we have studied previously in chapter 2. And method B is more of a titration technique. Okay, so that's how we actually connect the previous parts of the chapter with this part. The parts that we studied yesterday on the basis of soluble and insoluble salts, or even before that, we studied the characteristic reactions of acids with metals, bases, alkalis, or metal carbonates. That's how we connect them. Okay, so keep in mind in this specific part of method A, we're going to handle with the acid reactions with metal, with bases are insoluble. These were the soluble one, bases are insoluble, and metal carbonate. Okay, so I hope that clears
Yes.
everything up. That connects the previous dot with the current work. Also, you will be capable to understand this topic since you know about metals, bases, and metal carbonates already. Moving on. So method A, he clearly states acid plus solid metal or base or carbonate. That's why I made a mind map, so this heading and definition would be really easy for you. Now, we are all considering these three things because our method will be able to actually talk about them in a very good way and cater all of them under one umbrella. Now, our method can be divided into four stages, but really, in book right 5 stages gives you the head up for 4 stages. Take a look. We have mentioned 4 stages of hair, but stage number one, stage two, stage three, stage four. If I move on to the next page, we have a huge diagram on top. And right beneath it, you find stage five right over here. There you have. So yeah, it says 4 stages, but it puts up 5 stages. But let me tell you, it says 4 stages because if you look at the past papers, they usually want you to write in 4 steps instead of five. So we're going to study 5 steps, but I'm going to wind them up in four. How are we going to do that? Let's see. Let's start with the first step. I'll get to that point too. Now, stage one. In excess or more than enough of the solid is added to the acid and allowed to react. Using an excess of solid, make sure that all the acid has been used up. That's a very important point. So we need the excess of this solid, whether it's metal, whether it's base, or whether it's carbonate. It does not matter which one we are talking about. In all three cases, we need excess of the solid, but a less amount of acid. Why do we do that? Excess of all solid makes sure that all of the acid has been used up. Why do we do it? If the acid is not used up at this stage, the acid would become more concentrated when the water is evaporated later. Acid comes as an impurity, part one, point one, which we can write over here. Acid acts as an impurity. That's the first problem. That's why we take acid in less amount. Secondly, acid might attack filter paper slash apparatus. These are the two reasons because of which we specifically take excessive solid and less amount of acid and make sure all of the acid has reacted. Okay?
Yes, sir.
All right, great. Make sure you write both the points and you are writing them for the ATP paper. They're usually not a part of paper 2, they're usually not a part of paper 4 either. Get the point?
Yes, sir.
Good. When you're done writing, let me know.
Done, sir.
Okay,
Done,
let's move
sir.
on to stage. Yeah, right. Let's move on to stage two. I'm going to clear this whole thing up. Stage two is that the excess solid. This is one of the very good reasons why we were taking excess solid. Excess solid is filtered out at the next step. The step three is evaporation. Step four is crystallization or drying. These are the exactly 4 steps as crystallization. Remember, in chapter number 2, we took 4 steps of crystallization. Number one, formation of a saturated solution. Number two, filtration. Number three, evaporation. Number four, crystallization or drying. So this is all of it. So stage two is filtration, stage three is evaporation, stage four is crystallization or drying. But this is a little bit difficult to understand in words. So I'm going to move to the whole diagram and explain all of the 4 steps. Okay? Just give me a second. So getting back to the diagram, this diagram is divided into 4 steps or 4 stages, and they have simply written it as A, B, C, or D. Now, the A part itself has 3 bifurcations. That is because the first one is a reaction of acid plus metal. And since I've already explained this produces hydrogen gas, so there are the bubbles of hydrogen gas. So we warm the acid, we can use the Bunsen burner, but during the reaction, we don't keep the Bunsen burner switched on since hydrogen can easily catch fire. We switch off the Bunsen burner, add the excess of metal to the acid, and we wait until there is no more hydrogen gas given off or the bubbling stops. In the second part, if we are handling with the metal oxide, now metal oxide here specifically represents what I was calling a base earlier. Usually, all metal oxides, most of the metal oxides, not all, most of the metal oxides are bases. So add an excess of metal oxide to the acid, wait until the solution is no longer. We can always test it with a blue litmus paper. If it does not turn red, okay, it means that all of the acid has reacted. Since this produces salt and water, so we do not actually worry about heating. We can keep heating it during the whole process, right? Hydrogen was capable of catching fire, so there we recorded a precaution. Number three, this is metal carbonate reacting with an acid, and as you can see the bubbles in here, and they are marked out labeled as carbon dioxide, and we already know metal carbonate when reacts with an acid produces carbon dioxide gas, so that there we go, we can see it. Add an excess of metal carbonate to the acid, wait until no more carbon dioxide is given off, all right? So there we have the metal and acid reaction. All these three bifurcations are actually trying to produce for us the salt that we require. So this is all stage one. Moving on to stage two, we filter out the excess solid. That's why we initially put the excess solid. And the excess solid is going to left out as the residue on the top of filter paper, and filtrate will be a saturated solution of salt and water. We actually don't take the filtrate in a beaker, we take it in an evaporating dish or an evaporating basin, and we put it on top of a, a water bath. So water bath can be used for this purpose, and we can excess evaporate the whole of the water, the excess solvent. This step is known as evaporation. And finally, when crystals start forming, we let the solution cool or dry. This step is itself known as either crystallization, or it can be also considered as drying. Okay?
Yes.
Now, since the book has three stages and seriously talks about four, and there are also four stages in the diagram, so what I ask my students is that you can combine stage four and five in the book as stage four itself. You don't have to bifurcate stage five separately. So stage five is that the concentrated solution is cooled and would dry, let it dry. Sometimes we can filter off the crystals again, sometimes we can wash them a little bit again. But even if you don't filter them and wash them, you can simply dry them out. That's fine. If you ever need to do it for a higher temperature, instead of for water bath, we can also use a sand bath. Okay?
Okay, sir.
Then we get dried crystals. This example is actually for the dried crystals of zinc nitrate. So this is the whole process. The first method, method A, this is which is mostly crystallization. The second method is on page number 140, which is method B. And since the name is already written, it's a titration method. Now, before I move any further, I want to ask you, have you ever performed titration in school lab?
No, sir. But our
Okay,
teacher told us that we'll go in the lab this week, so maybe we'll perform it.
good, good. So before you move with this titration method, I am just going to clear you a few things about titration so that you can understand the whole thing easily. Now, titration is actually a neutralization reaction. We use acid and alkali. Why do we have a separate process for alkali? Because all the examples we were considering on the previous page were insoluble in water. The metal itself, the metal carbonates, the metal oxides, they were all insoluble. Alkali is the only soluble example. For soluble stuff, we have a different process, And for the insoluble ones, we can easily perform crystallization. That's why titration method is for the soluble parts and alkali are the soluble bases. That's why. So neutralization, acid, alkali, for example, sodium hydroxide. We can also use a soluble carbonate. That's fine. Both the reactions and products are colorless. So in that case, we need to use an indicator. The indicator will tell us the neutralization point or end point when all of the acid has been neutralized by the help of the alkali. Now, before I explain any of the parts, let me get you familiarized with the apparatus we are about to use. You're familiar with the beaker. This one is burette. Burette is an elongated glass-made structure with a tap at the bottom. Burette's width is very thin, and which is why burette is one of the most accurate equipments in lab. You might want to note it down. This is most accurate equipment, right? Since we're talking about measuring the volume of liquid, so its accuracy is all about volume of liquids. Also, pipette is, as you can see, has also a thin width. So pipette can also be considered as a very accurate equipment. As per the flask or the beakers, they may contain a larger volume of liquid, but they are not accurate. They are least accurate uh, equipment in lab. All right. This kind of uh, comparison between different kinds of apparatuses that we commonly use in lab for measuring the volume of a liquid and their accuracy or how much volume they can contain is an important part before we start off an experiment like this. Now, burette is the only one which has a tap at its bottom. Pipettes, beakers, flasks do not have this kind of leverage. Again, they're not designed this way. Are we clear?
Yes, sir.
Okay. Do you have the hard copy of the book in front of you?
Yes, sir.
Okay. I would like you to open page number 140 and keep the diagram in front of you. I'm going to go through the words and you're going to keep the diagram in front of you. It would be easier for you to understand the whole thing. Okay. I
Okay,
won't be
sir.
going back and forth. I just want to finish it up as quickly as possible. Now, the method is divided into three stages and they're pretty simple. In stage one, what we do is that we take the acid solution and we pour it into a burette with the help of a beaker and a funnel. The burette is used to accurately measure the volume of solution added. A known volume of alkali solution is also placed in a conical flask. For this, we use a pipette. The pipette also delivered a fixed volume accurately. Don't forget, pipette delivers a fixed volume and that it does accurately. Fixed volume means pipettes are designed to deliver a very specific volume and not more or less than that usually. Okay. However, if you want to take less than that, that's possible since the capacity of pipettes are less, like 10 cubic centimeter, 25 cubic centimeter, you can't take much of it. So a few drops of indicator, for example, phenolphthalein or methyl orange can be added to the flask. Remember, phenolphthalein is at a disadvantage. It shows us a pink color in the alkaline system, but for neutral and acidic, for both of them, it shows us colorless. However, methyl orange can be a much better option. Why? Because methyl orange can give us three different colors: red in acidic, orange in neutral, and yellow in alkaline system. Okay. So moving on, stage two. The acid solution is run into the flask from the burette drop by drop until the indicator just changes color from yellow to orange. Having found the endpoint for the reaction, as soon as it turns orange, we stop the process, we stop the burette, and we note down the volume of acid that has run into the flask. Experiment is then repeated without the indicator, and the same volume of the alkali is used in the flask. The same volume of acid, as noted in the first part, is then run into the flask. Alkali first, acid after. This time you're not going to use an indicator. So alternatively, activated charcoal can be added to remove the colored indicator. The charcoal can then be filtered off, but it's better not to use any indicator. If you're not going to use an indicator, what you can simply do is to go with the process of crystallization after. This is the C part. In stage C, really, what we can do is that the salt solution can be evaporated for its water content, cooled to form crystals as described in method A. So stage 3 is similar to the crystallization process described in method A, which means the solution has already been formed. So you go ahead, you filter it up, you evaporate it, and then you finally try to get pure crystals. Fair enough.
Yes, sir.
Now, the colors I've already explained are also given in figure 5.25, or A part or B part. They give you an idea how the methyl orange shows color in acidic and alkaline medium. However, it can also show a neutral color, which is explained in an arrow over here, which is orange. In case of phenolphthalein, that neutral color is also colorless. So is the color of the acidic medium, which comes as a disadvantage. However, I suggests that the kind of dilution we use for titration, this can't really be purple. Since we dilute acids and alkalis too much so that they don't affect us in case of an error or a mistake, this comes as a pink color and not as purple. Okay,
Yes, sir.
this finishes 5.9 for us.